Hello everybody, welcome to today's maths video. Today's video is going to be how to solve three simultaneous equations using Gaussian elimination. So let's get straight in. The video is going to be based on the example you can see here on the screen. So we have the three equations that we're going to solve at the same time in order to find the three unknown variables x, y and z. So before we solve them, let's go through a bit of a quick summary of the actual method. So if we just use three generic equations there, using just a notation a, b, c up to I, and capitalise a, b and c for the constants, the first step would be to form an augmented matrix. Now, this is just a matrix essentially that allows us to manipulate rows, each component of a row together. So all we've done, you can see in the x position, in the x column should I say, we've taken the variable, the constants from each of our three simultaneous equations, so a, d and g, and we've just put those in the x column. In the y column, we've done the same. We've taken the constants b, e and h, and we've put those in the y column. Same for z, and same for the constants. So that bit's really simple. Essentially all we're doing is taking out the unknown variables and letting those represent each column, and putting the constants before them into the matrix. Why do we do that? Well, from this position we can manipulate, using Gaussian elimination, the equations to get to a point where we have these three zeros in the bottom left of the matrix. And the reason for that is that when we reform the equations after to solve them, you can see that we'd have on the third row, we'd have 0x, 0y, and we've actually just got I1z. In the second row, we'd have 0x, y, well, our leaves was just with e1y and f1z. And from there, it's really easy to solve for x, y, and z, because in the third row, the third equation, sorry, all we need to do to find z is just divide c1 by i1. And once we have z, we can sub that into equation 2 and easily solve for y. And once we have y, we can easily solve. We can sub those easily into equation 1 in the y and z positions to find x. So they're the steps essentially. So we're going to work through how to form the augmented matrix, how to manipulate the matrix by adding and subtracting the rows to get the three zeros in the bottom left position in that triangle. And then we're going to reform the equations and solve them. So let's have a look at the example that I showed you before. The equations that we'll be working through are x plus 2y plus 3z equals 40, 3x plus 7y plus 2z equals 53, and 6x plus 3y plus z equals 43. So the first step, like I've said, is going to be to form our augmented matrix. So let's take a blank matrix. Let's label the x, y and z and the constants just for now, just for good habits and just for practice. If we look at the first equation on the left hand side, x plus 2y plus 3z equals 40. All we're doing, like I've said, is taking the constants before those variables and filling in the matrix. So in the x position, so this will be row 1 column 1 now, we've got 1x, so we'll just put a 1. In the same equation we have 2y, so in row 1 column 2, let's put our 2, and we have 3z, so let's put 3 there in the z column. And then for the constant we've got 40. So that's all we're going to do, and if we do the same for each equation, we'll end up with a matrix looking like this. So the second equation gives us 3, 7, 2 and 53 in the matrix, and the third equation gives us 6, 3, 1 and 43 in the matrix. So that's our augmented matrix form. That's the first step complete. Now let's look at how we actually manipulate that matrix to get what we're aiming for, which is the three zeros at the bottom left. So first step here, to make it easier, is we're just going to name the or label the rows of the columns, obviously row 1, row 2 and row 3, as is the correct notation for them. Then we're going to aim first to get zeros in two positions you can see now in red, which are position is row 2 column 1, row 3 column 1. So we're going to try and replace that 3 and the 6 with the zeros. How can we do that? Well, if we take the third row and from that we subtract 2 times row 2, you can see that in the first position we'd have 6 minus 3 times 2 gives us 0. So we know there that we're going to end up in row 3 with a 0 in row 3 column 1, which is what we're aiming for. But we have to do it for each component. So in row 3 column 2 we'll take away 2 times 7 from the 3. In column 3 we'll take away 2 times 2 from 1, and in the constant column, the fourth column, we'll take away 53 times 2 from 43. And that will leave us with the matrix we see here. So all we've done is taken away 2 times row 2 from row 3, and it's allowed us to change, by looking at each component, we've changed each of the component values to a position where in the first column of row 3 we have a 0, and we're on the right track to get a triangle of zeros in the bottom left. Next step is we're going to have a look at replacing the 3 with a 0. Well, how can we do that? Well, if we look at the matrix, we can see in the second row where we want the 0, we have a number 3. Well, how do we get rid of that? We can't use row 3 because taking or adding 0 from it is going to leave 3, so we have to use row 1. And what can we do? Well, if we take 3 row 1s away from it, we'd have 3 times 3 gives us 0. So we'll do just that. Let's look at each component. 3 minus 1 times 3 is 0. In the second column, 7 minus 2 times 3 gives us 1. In the third column, 2 minus 3 times 3 gives us minus 7. And in the fourth column, 53 minus 40 times 3 gives us minus 67. So we'll write that in. And now you can see we're on the right track. So we've got 2 zeros in the right position. And the last thing we need to do to get that the triangle of zeros, is try and eliminate the 11 here. So, what an important thing to note before we continue is the reason we've gone for the zeros in the first column first, as opposed to getting the 11 to become a 0 before the other two, is that now we can manipulate that third row to remove the 11 and have a 0 without it changing position row 3 column 1. So what I mean by that is we can now do row 3 plus 11 row 2, and that will give us a 0 in row 3 column 2, and it'll also keep a 0 in row 3 column 1. However, if we wanted to use row 1 here, for example if we did row 3 plus 5.5 row 1, that would give us a 0 in row 3 column 2 where the 11 is, but where the 0 is at the bottom left, adding on 5.5 to 0 gives us 5.5, so we'd undo the hard work we've done in getting that first 0 there. So the thing to do is get 2 zeros on your left hand side first, and then go to the bottom middle row 3 column 2. So like I said, let's work through it. If we go through row 3, and we'll add on 11 row 2. Like I've said, you can see that in the first position we just have 0 plus 0 is 0. In the second position, that's row 3 column 2, minus 11 plus 1 times 11 gives us 0. So we can see there the 11 is going to become a 0, and we're on the right tracks. You can see that there now in that matrix on the right hand side. In the third and fourth positions, all we've done is the same as previous, minus 3 plus minus 7 times 11. In other words, minus 3 minus 77 gives us minus 80. And in the constant column, the fourth column at the end, minus 63 plus minus 67 times 11, and that gives us minus 800. So that now is our augmented matrix manipulated into the position we want with 3 zeros in the bottom left position, so that's position 2, 1, 3, 1 and 3, 2. From that then, it's really easy to just take out the equations in the same form that we've had before. We know we have the x, y and z columns, so for the top row all we do is we rewrite the equations, and we'd have 1x plus 2y plus 3z equals 40. The second row in the matrix we'd have 0x plus 1y minus 7z equals minus 67, and in the third row 0x plus 0y minus 80z is minus 800, or simply the equations that you see at the bottom there. Well, what's the point? Look how easy it is to solve those now. The bottom equation just contains z. So all we have to do is if we divide both sides of that by 80, it eliminates the 80 on the left hand side, the minus 80 on the left hand side, and leaves us with just z. Well, minus 800 over minus 80 is 10, so we can see there that z must equal 10. Next step, well, let's sub it in the next equation up. If we put it in there, we can see that we actually just have the y variable left, because we know what a z is, we know the value of it, so if we put that in, we've got y minus 7 times 10 equals minus 67, or y minus 70 equals minus 67. If we add 70 to both sides, you can see we'd have y equals 3. Same again now, let's go up to the top equation. We have our value for y and we have our value for z. All we're going to do is pop those in the correct positions, and you can see that we get x plus 2 times 3 plus 3 times 10 equals 40, or in other words, x plus 36 equals 40. Taking 36 from both sides gives us a value of x equals 4. So that's it, we've worked through the steps fairly easily there. We have formed our augmented matrix, manipulated it by adding and subtracting the rows from each other to get zeros into the 3 bottom left positions of the matrix, from which we just need to rewrite our equations in the form you now see at the top left, and easily solve those for x, y and z. Now just to be sure, let's check the values. The reason it's really important to check with Gaussian elimination is that, as we've seen in the matrix on the previous page, you can have examples, you can end up with values that are really small fractions or massive numbers. For example, you've seen we had minus 63, we had minus 800, and it can get really confusing sometimes. And sometimes the numbers are so odd, or the fractions are so far-fetched, should I say, the sort of thing you wouldn't expect in an exam. You wouldn't expect in an exam to get a fraction like minus 27 over 350, for example. So when you've got those fractions and you've got your answers, it's really important to check that the fractions were actually the way they should be, and there hasn't just been any, well, the written version of typos, should I say, any minor mistakes. So let's check here. All we're going to do is take our 3 original equations. We know the top equation we've used already, and that was in the matrix throughout in the top row, so we're not going to use that. We're going to take either the second or the third equation. So let's take the second one, and simply all we're going to do is plug in the x, y and z values. We know that 3x plus 7y plus 2z equals 53 then becomes 3 times 4 plus 7 times 3 plus 2 times 10. If we add those up, we've got 12 plus 21 plus 20, which does in fact equal 53. So we know that our answers are correct. Just like that, we've worked through them all. We've got our 3 answers, we've checked it, we know they're correct. And that's it. They are the few simple steps to solving 3 simultaneous equations with Gaussian elimination. So thank you very much for your time. If the video's helped, please give it a like. Share it with any of your friends who may be struggling with the topic, or who may be new to learning the topic and you think they could just do it with a hand. If you're struggling with anything in this video, or any other topics that you're learning at the minute, please just comment below and I'll do a video or reply to your comment to help with your struggles. And then if you want to see more, please subscribe. Thank you very much, and goodbye.